Here we are on page 2 of Trig Functions, Equation Identities, Addendum. First we're going to look now at a graph of some of the reciprocal trig functions. So first we'll take the case of cosine and its reciprocal, which is secant. Okay, so secant is 1 over cosine, and we just learned how to graph some reciprocal functions in the functions chapter, right? So let's draw first cosine. So cosine, remember, if we consider that it ranges from 1 to -1, 1 to -1, it looks kind of like this. So like the width of this domain here is going to be -2 pi to pi. So this is -2 pi, and this is +2 pi. And so cosine basically looks like a big cursive V, and there's one here and one here, right? And so that's basically the cosine curve. And if I wanted to find the, if I wanted to make a graph of the reciprocal function 1 over cosine, remember the rules to do that. First we find the invariant points. The invariant points are all the y equals 1 and -1 points on the curve. Those are where the reciprocal functions will intersect with the original function. And besides that, the close, whenever the reciprocal, the function, the original function crosses the x-axis and y is equal to 0, then we know that the value for 1 over cosine, or the reciprocal function, is going to be 1 over 0, which is infinity. So, or infinity or -infinity. So basically, all these 0 crossing points of the black function are going to turn into asymptotes for the purple function. And then anytime the black function approaches the x-axis, then the reciprocal function is going to approach the asymptote. So do you see how I can make they look like parabolas, but they're not parabolas, because parabolas, go to the left and right without bound, and these are obviously limited by the asymptotes on the right and left. And actually there are going to be invariant points here and here also, so I could also draw half curves there. So basically that's what the reciprocal function for cosine looks like. On number 6, we're going to do the same thing with y equals tangent x. I have graphed the original function y equals tangent of x in black here. It goes from -2 pi to 2 pi. Remember, the width of one tangent cycle is basically pi, and it's centered at the origin. So the first one is right here, and it's got asymptotes at pi over 2 and -pi over 2. And so now we need to do cotangent, which is the reciprocal function for tangent. And basically we're going to mark all of our invariant points at 1 and -1. So there's one there, and there's one there, there's one there, and there's one there, there's one there, and there's one there, and there's one there, and there's one there. Okay, so that's where our reciprocal function is going to cross the original function. And then we're going to have asymptotes every time the black function crosses the x-axis. We are going to have a purple asymptote, and so I'm going to draw those here. There's actually one on the y-axis too. Okay, and every time there's a black asymptote, that would be where the purple function crosses the x-axis. So actually, I'm going to draw a purple dot every time the black asymptotes cross the x-axis. Okay, and so basically, it will look kind of similar to the black function, but instead of having an asymptote at these points, it actually crosses the x-axis, and whenever the black curve hits the x-axis, the purple has an asymptote, so everything is kind of the opposite. So it actually looks exactly like a tangent function. It's just flipped and out of phase. So, and when I say out of phase, it means they don't cross the x-axis at the same point. So pretty weird looking, right? And I guess it kind of makes sense because remember, the tangent function is sine over cosine, right? So if you have sine over cosine, 1 over the cotangent function is actually cosine divided by sine. So you would end up something very similar to what you started out with, because remember, sine and cosine, they are functions that look pretty much alike. They're just out of phase. So it makes sense that the cotangent is out of phase with the tangent. Okay. Let's move on to 12H, inverse trigonometric functions. So remember how in this video a couple times I've said inverse function, or inverse sine, or inverse cosine, or the inverse of the sine function, and I've caught myself and I've replaced it with reciprocal function. Because we really need to be careful now that we know what a reciprocal function is, now that we're figuring out what reciprocal functions of sine, cosine, tangent are, we need to be careful about using interchangeably the words inverse and reciprocal. Now reciprocal is definitely taking a fraction and putting it upside down. The denominator becomes the numerator becomes the denominator. Inverse is a little bit more vague, right? Sometimes we say invert a fraction and we mean we take the reciprocal, right? And we already have a terminology for inverse sine, inverse cosine, inverse tangent, meaning a function which does the opposite of sine, cosine, and tangent. So like normally the input to sine and cosine tangent is an angle and the output is a fraction. And inverse trig functions such as inverse sine, inverse cosine, and inverse tangent, you actually give it the fraction and then it gives you back an angle. Okay? So rather than writing inverse trig functions as sine to the -1 power, cosine to the -1 power, and tangent to a -1 power, which can be confused with reciprocals, mathematicians more formally refer to these functions as arc sine, arc cosine, and arc tangent. Okay? So below here we have the definitions for arc sine, arc cosine, and arc tangent. Basically, you do variable interchange. Do you see how the x's became y's and the y's became x's? Variable interchange, because what we're doing is we're reversing the direction of the function. Instead of going from angle to a fraction, now we're going to go from fraction to an angle. The range and the domain of the arc sine, arc cosine, and arc tangent functions, you can see them here. So the input to arc sine is going to be a ratio from -1 to 1. The output of arc sine would be an angle. And same thing with arc cosine. You input a ratio from -1 to 1, and output comes a angle. Tangent, you can put in any ratio, which, remember tangent ratios can go to infinity and negative infinity. So basically, the ratio you put in can be any real number. Out comes an angle. Now, what's a little bit different than what in the other direction is, when you do arc sine, arc cosine, and arc tangent, the output you see are like 3 different intervals. They're not even the same intervals, right? Arc sine looks like the output angles are in the first and the second quadrants. Now, the first and the fourth quadrants, right? So like it could be this quadrant or it could be this quadrant for arc sine, right? And arc cosine, the 2 quadrants that the output might be in, are the first and the second quadrants. And tangent, last of all, is going to be the same as arc sine, so in the first and the fourth quadrants, okay? And now what we're going to do is we're going to take a look at this last statement. Why are the ranges for the inverse trig functions restricted? Okay, that is a really good question. Now, if you look at a inverse function, remember how you find graphically the inverse function. So let's say that we have sine, for example. Sine looks like this, remember? So let's take the inverse function of sine. Remember how you find the inverse function? First you draw a diagonal line through the origin, and then what you're going to do is you are going to invert this red function about the green reflecting line, okay? And basically what you end up with is you end up with something that looks kind of like this, right? And the problem with this blue relationship is that it is not a function. Remember that the definition of a function is you only have one y value for each x. If you give it an input, it's going to give you one output that relates to that input. It's not going to give you multiple outputs. And this blue function has multiple outputs for one input. Like let's say that we put in x equals 0. What are the blue outputs? Well, there's one here, there's one here, there's one here, there's one here. So there's a lot of different outputs for the same input, which makes sense, right? Because when we talk about trig functions, like infinitely many angles have a sine of 1, for example, right? It's not just 90 degrees. It could be 90 degrees plus 360 degrees. It could be 90 degrees plus 720 degrees. It could be 90 degrees minus 360 degrees. So how do they make it so that the arcsine, arccosine, arctangent are functions and not relations? How do they make it so there's one output for every input? What they do is they cut off part of the function. So they just consider like this part of the function, for example. If they only consider this part of the function, then they've succeeded in making a function which has one output for every input. And so you can see that, like for arcsine, for example, they actually consider only negative pi over 2 to pi over 2 as valid outputs for the trig function, the inverse trig function. So basically what they're doing is they're saying from here to here, those are our valid outputs. And so for each function, they did kind of the same thing, and it turns out that what they did for sine and cosine is like two different things. Because, like, let me draw cosine for you. Cosine, remember, looks kind of like this, right? And if you invert this function about the green line, then you're going to get, let's see, something like this. Okay, and you can see that is not a function, right? So let's see, how are we going to restrict cosine? Well, we can't really restrict it the same place we restricted sine, because if we did it here, then it's still not a function, right? Because we have repetition there too. So what we do is we're going to choose this part here. Okay, so that is why even the range of arccosine is not even the same as the range of arcsine, because if we did make it the same as the arcsine, then it would be not a function. Okay, and the same thing with arctangent. Arctangent, actually, we're able to use the exact same range as arcsine. It works out. Okay, that's it for this page.